Um, hey everyone, so today we'll be solving the problem point selection, which is a part of educational round 184. Yeah, problem says that Alice and Bob are playing with points on an XY plane. Initially, there are n points on the plane, and the ith point is located at xi, yi and has a cost of ci. The game basically consists of two stages. In the first stage, Alice selects some points, possibly none but not all, and removes them from the field. Then Bob draws a rectangle with sides parallel to the coordinate axis. Yeah, so Bob draws a rectangle with sides parallel to the coordinate axis such that all the remaining points lie inside or on the boundary of this rectangle. And this rectangle can degenerate into a line segment or even a point. After the two stages are complete, the game ends and the total score is calculated. So the total score of the game is the sum of costs of removing points by Alice and the perimeter of the rectangle drawn by Bob. So Alice wants to maximize the score while Bob wants to minimize it. So we have to determine the total score of the game if both Alice and Bob play optimally. The perimeter of a rectangle is equal to the sum of lengths of all the four sides. Therefore, even if the rectangle degenerates into a line segment of length k, its perimeter will be 2 times k, and the perimeter of the rectangle that degenerates into a point is 0. So these are some constraints on the upper bounds of different values. The maximum size of the set of points that we have can be 3 times 10 to the power 5, and the coordinates can be as big as 10 to the power 15 but will be greater than 0, so lying in the first quadrant. And the fourth line contains n integers, which is the cost of each and every point that lies in 10 to the power 9. So these are some possible test cases. I think we can go through them. So yeah, so I think this makes the problem a little bit clear that Alice wants to maximize the score while Bob wants to minimize it. And let's define score in a different way than the problem state, or in a similar way but an easier way. So let's say that R is a set of points that are left after Alice has made their selection. So R is the set of points that are left after Alice has chosen a particular set of points. Right. So what will be the cost? Well, one part, one contribution to the cost will be by the points that Alice has chosen. So that will be uh, sum of Ci for all the points lying in a P, that is basically S minus R, and S denotes the universal set of all the points. And then we will add to the parameter PR, let's call it PR, which is the perimeter of the rectangle that basically provides a cover for all the leftover points. And this is the minimum perimeter of the rectangle. So this will be our cost. So this is something that can be easily calculated from the leftover set. But how do we think about choosing a minimal parameter? So one thing we can observe is that, let's say that we have a particular set of coordinates that are left. So something like this. All right. So let's say we have a coordinate like this. So how do we form a rectangle such that it provides a minimal parameter and covers all the set of points? So if we try to draw that rectangle, right, it will be something like this. Starting from here, we'll go here, and then we'll start from here and go till here, and then we'll start from here and go till here, and then we can start from here and go till here. I think this rectangle is the rectangle with the minimum perimeter and covering all leftover points. So, so how can we define this perimeter? Well, it's nothing but if we take this, what is this point? This point is basically the minimum xi and yi for all xi yi that belongs to the removed set. This is what that is, right? We are choosing the minimum xi and the minimum yi. What is this point? This point is basically the minimum xi comma maximum yi from the set xi comma yi that belong to the remove set. What is this point? This point is basically the maximum of xi comma minimum of yi that belong to R. And what this point is maximum of xi comma minimum maximum of yi that belongs to this set. So we can see that while forming the perimeter from the removed set of points, we only care about 4 coordinates amongst those set. So that would give us the minimum perimeter of the rectangle that provides a coverage for the entire set of points that are left. So the 4 coordinates that we care about are the minimum xi, the maximum xi, the minimum yi, and the maximum yi. These are the points that are enough to form a rectangle with the minimum perimeter. So how will they contribute to the perimeter? So we can define PR as 2 times maximum of xi minus maximum or minimum xi plus 2 times of maximum of yi minus minimum of yi. Why is that? Is because if you try to calculate the length of this side, this is nothing but maximum of xi minus minimum of xi, and this side will be the same as this because they are parallel and the starting coordinates are same. So we do 2 times maximum of xi and maximum of minimum of xi, and similarly for the y-axis. So we can rewrite these as 2 times maximum of xi plus 2 times maximum of yi minus 2 times minimum of xi minus 2 times minimum of yi. So we can see that this is the perimeter that will be formed from the set that is left. So for all the set of points that belong to the universal set, they have two choices. Either they are removed by Alice, that would add to a cost Ci, or they participate in the leftover set, which is R. So these are the two choices that all the points that are given to us have. So when they participate in the leftover set, we can expand on how to calculate the perimeter and the cost. So one thing we know is that This is how the points contribute. So for a particular point, it has all these choices of contribution to the minimal parameter that Bob has to select, because that is the only control that Bob has. He only has control to minimize the cost by minimizing the perimeter, and the way to minimize the perimeter is by choosing these four scenarios for a particular coordinate. So each and every coordinate, um, if we see in our rectangle, can contribute to forming the rectangle by taking four possible places. So a coordinate while we are forming the rectangle can be present or contribute to the minimal parameter in these possible four ways. Hmm. So how do we check for if uh, a point belongs to a particular set or not? So since each of the point has four choices, basically it can contribute in four possible ways in the candidature, not exactly being a part of the perimeter. So uh, when we have only one point, that point is contributing to all the possible four cases, right? Because when we calculate the minimum xi, the maximum xi, the minimum yi, and the maximum yi, when we have only one point that belongs to R, it contributes to all four of them. When we have 2 points, it may or may not contribute to two, three, four, or it may even not contribute to any of them. When we have 3 points, we'll have a similar candidature, and this goes on. So each point can be a candidate, and we can calculate that by going through a set of particular points. But there is one catch, that it might have happened that a particular set of points is already occupied. So if we try to assign that point there, and then that would cause us to have a worse answer. So for a particular point, we only have the choices amongst a set of 4 points that have already not been occupied. So for example, let's just say that the current scenario we have is, uh, let's just denote these sides as 1, 2, 3, and 4. So we know that each of these points in the parameter is contributing to a particular side, right? As we can see here, each possible scenario belongs to a particular side. So let's just say that let's just have this. So let's just define this as maximum of xi. Let's define as minimum of xi. Let's just define this as maximum of yi. Let's define this as minimum of yi. We can just assign these any values. This will be -2, this will be -2, this will be +2, and this will be +2. So each of these particular xi or yi can take any of these possible scenarios. But let's just say that these two sides are already occupied. So if you're trying to choose in this type of set where first and the third is occupied already, then we only have choices for 2 and 4, and we can see amongst all these subsets where we want to give them. So we have a set of 4 points. So this inclinates us to a DP of subset problem, right? Because we have a set of 4 points and we have to assign the leftover sides from a particular set. So let's come to the solution now. This was the explanation of what we actually have to do, right? And I think a giveaway for DP was also this thing that we have here, the universal set. So each point can have two choices. So this was also a giveaway for DP that I thought about. So we can define a DP as a mask, and this mask can take a value from from 0 to 15, denoting 15 denoting all four sides are occupied. So each bit is denoting a particular side. We can just decide it to be anything. Doesn't really matter. Uh, but for just for simplicity, I'm taking this as left. I'm taking this as right, this as down, and this as up. These denotes all the sides contribution. So this will be minus 2xi, then we'll have plus 2xi minus 2yi plus 2yi. So we can form a dp of mask, and dp of mask basically indicates the maximum answer if we have selected a subset mask of sides. So for each point I, comma yi, we have two choices. If we do a ci, then it would be nothing but dp of mask, comma I will be dp of mask, comma I. Let's just say it's ndp of mask, comma idp of mask, comma I plus ci. Otherwise, we will do our logic for the bits. So the other case is we have a set of r, right? So for every single bit, um, we have certain amount of choices. So we'll go through the entire mask and we will just see how many sides are available. So let's just say that we have a mask 1010. What are the sides that are available for us to assign or point to? So the possible candidate sites are this one and this one, which is nothing but uh, 1 1 1 1. We can just take an and with the reverse of the mask. So this would be 1 1 1 1, and the negation of this mask would be 0 1 0 1. So that would give us 0 1 0 1, and this will be the set of leftover sides. And amongst these set, we can basically our xi comma yi can be a candidate for any submask of this set. So it can be a part of this set, it can be a part of this set, or it can be a part of this set. And so this is how it can be occupied. So this basically is the final solution. In the end, we can just return dp of 15, which would denote that we have occupied all the sides of the rectangle. So I think we can come to the code now. I'll explain the code in more detail. I think it would be more clear then. Um, yeah, yeah. So this is the code that we have. Oh. So I have some comments here. So this denotes the total sum of all costs. I think we don't really need it now. Hmm. It's just a way to calculate the contribution of Alice. So Alice basically contributes total minus C of I that belongs to the set of R. So we can also do it by total minus the total set, but I just figured out it would be easier just to include that in DP here, just as CI. So this is how I have done this. We can also do, I think, we can also have a DP of n comma 1 to the power 4 because 2 to the power 4, because this will be for each and every index I. But this is just a space optimization that we can do by creating a temporary DP table. So DP, yeah, I have mentioned it here. So this denotes this denotes the maximum possible answer for a particular selection of sites. Uh, so selection of side I means that a particular state. So 1 0, which is basically 1010 is basically left and the bottom side as we defined earlier. And then in the end, we can just return dp of 15, which will be the answer. So dp of 0 is when we have selected no sides. So degenerate rectangle at a particular point. This is what the problem states, and this is a good base state anyways, almost for every problem. So we can iterate through every single I, and then this is just an optimization that I am doing. So basically, what this means is that let's just say we have a point, for example, um, let's just say we have xi and yi, and we have a particular selection of sides. Let's just say 1 1 1 0, right? So this add of uh, a particular mask denotes that how the point is contributing in that mask. So let's just say that if we take this mask 1100, so it will contribute as 2 times x of I plus 2 times y of I minus 2 times y of I. So this is basically a total calculation we are doing for all possible scenarios that this point can take for all possible masks. So yeah, he can be a candidate to any of the sides. So we can just iterate through it. And this is just something we can also do while defining the submasks, but it's same as doing it. It's just to reduce some complexity here. So then we can reset our NDP array, typical thing that we do in space optimization. So then I'll go through each and every mask. If the mask is not defined yet, so we'll just continue. Otherwise, this is a case when we decide to choose a point. So basically, this point is chosen by Alice. So we directly add the cost. Otherwise, we choose the leftover bits. So this can be seen by 15 is basically 1111. We can take an and, for example, if this was the mask, then we can just take a negation of this mask, which basically denotes the opposite bits. So 1111 and 0001. That would give us 0001. So basically, this is the set that we have. So we'll iterate for all the submask of the leftover sides, which is 0001. We'll have a new mask, which will be the mask that would contain the submask, and the answer would be dp of mask plus the contribution of this submask to the overall sides that we have already calculated above. And then we'll just swap the dp and ndp, and in the end, the answer will be dp dot back, which is dp of 15, indicating that we have formulated a rectangle because we have to form one rectangle at least because one point will be left by Alice. She cannot choose all the points. So this basically denotes that hey, we have formulated a triangle. So this is the answer for that. So yeah, I think this explains the problem. If you have any questions, you can just put them in comments. Uh, I think the hardest thing to grasp in this problem is probably this side logic. I think if you can probably go through this or maybe this example. Uh, no, this one is not great. We can probably tweak some values in this example and change some y's and x and do a try, and that would make this more uh, understandable. So yeah, this is the problem. That worked for me. This is the solution that worked for me. So yeah, this is a good problem. I don't think there was much of geometry involved in this. This was basically DP and bit masks and also submask kind of thing. I don't know how they have implemented it. Maybe we can just check it. What has blood test done? Hmm, I don't know what the hell is this. I think this is also a pre-calculation just like us. Yeah, it is. It is actually just what we are doing, but in a smart way. Yeah. So it's a good thing to pre-calculate because we don't have to then calculate it here. We can do it here as well, but so he is also iterating through each and every subset. I can also move my pre-calculation above. Mm, yeah, I could have done that. It would make my solution a little faster. Oh, he's using two-dimensional. Yeah, it's same. Yeah, it's same. Then he is filled. Yeah, this is also same. Oh, this is actually a better way in doing a negation. And then he's going through each and every submask. And in the end, just return all the. Yeah, this is pretty similar to what I did. I think my solution is a little less intelligent than him, but uh, yeah, yeah, he wrote a very clean solution. Well, it is what it is. Uh, so yeah, that's it for this problem. Let me know if you have any doubts. I'll reply to the comments. So yeah.